Thank everyone who's joining today for taking time out of your busy days, and if it's beautiful where you are, taking time to spend time with us to learn a little bit more about cold quanta and some of the things that we are doing in the context of the quantum revolution. I want to just give a shout out, and you'll hear reference to some of these. We have several future webinars coming, as Diane mentioned, one on quantum signal processing. We will also be giving some additional ones on positioning systems, clocks, laser cooling, and more. So overall, what we're going to talk about today is I just want to give a little background. Dana, Bo, and Seth, if you've attended some of our previous webinars, have given a really nice background on cold atom systems, how they work, and even some of the specialized instances of that with Bose-Einstein condensation. So I'll keep it very brief, but just as a setter, set the tone for this presentation, just touch on that a bit, and then kind of shift gears a little bit and talk about the investments being made in quantum, what are the markets, and what are those opportunities. And the specific opportunities we'll talk about today will be around inertial navigation, clocks, and quantum computing. So what do we mean by the second quantum revolution? Really, what was the first quantum revolution in the first place? Well, folks today, you're maybe used to having, maybe a CD player which has a laser diode inside. That is a fundamentally quantum device with electron hole pairs and electrons combining from an upper state to a lower state to make a photon. These also involve coherence of the light. When you wander into a room, a photodiode will detect the fact that you have an infrared signature and actually turn on the lights for you, and that's also a quantum device. But what's different in what we call the second quantum revolution is once we get really fine control of these quantum systems, these quantum particles, suddenly new things open up. And the big piece is superposition and entanglement. By slowing the particles down to nearly stopping them, what ends up happening through the Heisenberg uncertainty principle is the particles can interact, and you can start to do a whole host of things with these particles that were not previously available to us. And that's really what this is about. We've really made progress in these past several decades that have made it possible to do things that weren't able to be done before. Isolated atoms make an ideal quantum device. And just to give, again, a very brief overview, almost a whirlwind, and I encourage you to visit some of our other webinars, which will go into this in much more detail. Any given atom was characterized by having a unique energy spectrum. And what's characteristic of any quantum system is you have these quantized levels. So you have a bottom level or a lower state, and that's connected to an upper state, typically with a photon, but it can also be done with microwaves as well. And this allows us to store information or sense the world around us with these systems. However, in order for these systems to work well, they need to not move. When atoms move, atoms or anything is in motion, and that's caused by having a finite temperature. They're subject to Doppler effects, and they're no longer identical. So it's extremely important we make these systems cold to control them, and then they become identical, and then we can leverage we can leverage their properties better. So it's always a challenge to try to attempt to capture laser-based cooling of atoms in just one slide, but the fundamental here is that an atom can absorb a laser light that is tuned resonantly to the atom. And if you tune it just below the atom's resonance frequency, you can actually cause it to slow down. And so if the atom is traveling towards the beam, it'll receive more force than it does if it's moving away from the beam. And in doing so, we can produce a sample of atoms that is exceedingly cold. The photons themselves actually subject the atom to a tremendous force. It's thousands of Gs. So it's sort of remarkable to think that this little laser can actually be really wailing on the atoms to get them to stop. And we can bring them to a stop in about a centimeter. This technique is now routine and a standard technique in these types of quantum systems. It gets the atoms down to about 300 microkelvin, and that's kind of the upper limit. We routinely get them down to the tens of microkelvin, and last month Seth described Bose-Einstein condensate, which gets you down into the hundreds or tens of nanokelvins. This was such a remarkable discovery. It was awarded the Nobel Prize, as well as Nobel Prizes for follow-on work from this activity. So we're going to make a little bit of a hard shift here from the science and just kind of setting the baseline here and talk a little bit about what's going on in the overall financial side of things, the landscape. So there's really been, if you've read anything in the news, you've seen that there's been tremendous investments being made both in the US as well as in Europe. Billions of dollars. It's roughly about more than $16 billion across the globe. And big programs. The National Quantum Initiative program is a $1 billion program. The EU has a $1 billion quantum flagship program. The UK has several programs, $1 billion. China is spending quite a bit. Germany, all over. So this is not a comprehensive list. So the government is really putting a lot of impetus and energy into these quantum investments. Private investments are also happening. So this is venture capital. Just in the past 8 years, there have been 700 deals, venture capital deals, investment rounds closed, totaling over $1 billion. And these cover everything from communications to quantum computing to sensing and related instrumentation tools and software to support creating these systems. And then finally, larger commercial companies are making investments. They're less public. These are large public companies. But within each company, there's the very public companies who are working in quantum computing. But within the primes and a lot of major companies, there's efforts going on in communications, quantum sensing, all of the disciplines in quantum. I think it's without every single one of these companies has an interest, investment, and focus on the growth of these areas. And then talking a little bit about the commercial side of things, turning things, this is a little bit of a products or markets 101. So, but I think it's worth saying, you can look at quantum products and quantum technologies as being enablers for two very broad segments. And again, this is kind of business school 101, existing products. What can you do with existing products? Can you enhance them? And you can push the capability of what we can do today by tens to thousands of times better than conventional technologies. And then there's new products and markets. Quantum computing, quantum networking are a couple of brand new markets, but even in existing markets, there's going to be capabilities that have not been envisioned yet. So there's a lot of things that we just have not yet discovered, because these changes and the capabilities enabled by fundamentally entangled systems are quite broad. And this chart, this is a very conservative estimate of the growth of the quantum market. So, right now it's talking about being about a $500 million market and growing to well over 3 billion. And this is just a subset. This really focuses on the hardware aspects of quantum. We'll talk a little bit more in a later slide about some larger markets, but this is a large and rapidly growing market. So next, I want to talk about some of the opportunities available to us and kind of segment what are these, what is entanglement? What does that allow us to do? And we kind of broadly think of this in 3 different areas. Quantum sensing, this is ways of using these quantum systems to measure the world around us. Quantum computing, using these to compute, to do things we've never been able to do before. And then quantum communications, and I'll kind of break this down. So a little bit of a tree here showing some of the things that you can do. So quantum sensors, you can broadly say they can measure inertial, where are you, what's happening. You can measure the passage of time. You can make physical measurements, including magnetic fields, electric fields, even pressure. Some of the most sensitive pressure measurements can be done with cold atoms. And then quantum computing is also enabled here. And then quantum networking. You can think of communications as kind of 2 segments, being quantum networking, where you attach various quantum computers with each other, and then also secure communications, where you can produce a better or more secure way of communicating, and do so by using the fundamental nature of entanglement of the atoms. And the blue dotted line there just is simply to indicate that quantum networking and quantum computing are kind of entwined as very related topics and markets. So when I put this talk together, I ambitiously thought, hey, I'm gonna talk about all of these things because they're very exciting, and in fact, Cold Quanta has a hand in each and every one of these areas. But given the length of time we have today, we're just going to talk a little bit about inertial sensors, time, and talk just very briefly on gate model quantum computing. And I should mention, maybe this is the right place to do that. We will be, future webinars, as we mentioned before, will allow this sort of superficial look that I'm trying to give over these topics. Each and every one of these will get a deeper dive, and hopefully will satisfy appetite for additional knowledge and information about each of these areas. So the next piece I want to talk about is inertial sensing and the role that cold atoms can play there. So the motivation here is to navigate without GPS, and some folks call this assured position navigation and timing, sometimes called APNT. We really rely upon GPS in a huge way. These are actually very weak satellite signals that are reached on the ground, and they're readily overwhelmed with transmitters on the ground and being spoofed, even to the point where some of the spoofing happens very in an agile fashion, where you will slowly change a signal to make you think that you are somewhere else than you are, rather than just having a giant step change in the blasted signal saying where you are. So this is a sampling of some of the things that have happened with spoofing and even outages of the Europe's GNSS system. It's considered really a tactical weapon now because it is important. And within the Defense Department, all the branches of the U.S. DoD have called for ways to do improved accuracy without GPS. And a couple quotes here from the famous Ash Carter. I hate GPS. So there's a lot of energy. This is an exceedingly important, and to emphasize, this is important beyond even defense circles. This can affect some of the important early places or emergency vehicles, which are standard commercial. That's if a vehicle like that gets spoofed, someone's not going to get the help and aid that they need. So let's go in a little bit of detail. So how do you accomplish this? What's in this? So we show a standard large-size drone. I think this is a Predator, and inside that's going to contain what's called an inertial navigation system. And this box, its goal is to tell you where you are, what's your position, what's your heading, what's going on. So what's inside this thing? Well, inside of it is a inertial measurement unit. So within that inertial measurement unit, we'll talk about in a second, but there's an inertial measurement unit, an IMU. It contains a clock. Most of them actually contain a GPS receiver as well, and that's kind of the backup. And then you have to integrate the system so you can turn all of these widgets into an actual signal. Now, the circumstance we're talking about is we don't have the luxury of that GPS receiver. We have to figure out where the heck we are without the benefits of that receiver. So one more step here, the IMU actually contains an accelerometer and a gyroscope. And an accelerometer, I like to say, that measures jiggle. That measures if you make a change in where you're moving, it measures that. In fact, it can measure gravity, and that's one of the challenges, that you've got to be able to sort of take gravity out of it, yet be very sensitive to the change of the system. And then a gyroscope can measure rotation as a system rotates in space. And now the next is a tiny bit of an eye chart, but I just want to show you. Take your accelerometer, you take your clock, you take your gyro, and you're going to do some wizardry with it. So we are not going to go into this gray box of wizardry. I am not qualified to go through this. What I can say is the output of this wizardry is you take these inertial measurement systems and you provide an orientation. Where are you pointed in space? How fast are you going? And where are you? So that's how these things all tie together to tell you where you are, and to do so even without the luxury of GPS. So just talking a little bit about markets and putting these kinds of devices into context, navigation is actually a multi-billion-dollar market, a multi-billion with double-digit billion size market. Within that, we're just focusing on high-performance navigation. So these are the most sensitive applications that need the highest performance. Within that application, what supports that are accelerometers and gyros, which all by themselves, just these two devices for high-end, are about a $5 billion market. And I further break this down into the gyro itself and some of the technologies and the sizes of the markets for those technologies. And there's three technologies we show here. And as much as I'd like in this presentation to sort of do a deep dive and give a full discussion of each and every one of these, how these things work, we won't have time to go into that. But what I can say is that these are some of the most sensitive devices that are available today for doing measurements of rotation of a device. And the gyro is actually one of the most important elements inside an inertial navigation system. In other words, the gyro actually is the most important term as you try to understand where you are on the planet. And to say the future performance is going to demand IMUs based on cold atoms. So this chart is simply showing the kinds of technologies used for each of the markets. So we have sort of the lowest performance market on the right, consumer commercial markets, and moving all the way to long-range guidance and very precise navigation on the left. And fiber optic gyros are being used today for very precise gyros, but cold atoms will be the next way that we can do this. And I'll explain just briefly, kind of an overview, because we're going to have more talks about this in the future about how this works. Let me say one thing on this slide. You know, a fiber optic gyro or a ring laser gyro, for that matter, the way it works is you have a coil of fiber inside that gyro, and you send light in both directions. So you send it around counterclockwise and you send it clockwise. And those beams of light actually will interfere as they come out of that gyro. And that interference will change depending on how much you rotate the gyro. Because you've rotated a bit, you're going to change the phase of the counterclockwise versus the clockwise beam and produce an interference pattern. And that's what makes these very sensitive devices to measuring rotation. So keep in mind, you've got laser light and interference of laser light to generate that rotation. So to do this, and one more. So you know, this area are the target opportunities for cold atom-based measurements, the long-range navigation and very precise navigators. And we can think of these cold atom-based devices as providing discipline or long-term guidance for these systems, because they're based on atoms. Atoms are atomic, they're precise, they're perfect in the sense that they are generated by nature. There's no engineering defects to them. That allows them to provide an absolute reference for these kinds of applications. And we'll talk a little bit more about that in a moment when we get into the context of clocks. So this is trying to, again, pack a very complex subject into one slide. And again, I'll refer back to a presentation Dana gave about 2 months ago, and I believe we'll be having more discussions on this down the road. But the idea is that we reverse the roles of light and atoms. So we generate, in this case, a beam of atoms. And this can be done with samples of atoms, but we're just giving a cartoon to show kind of the easiest to explain example of atom interferometry. And then we use laser light. And that laser light actually takes the atom in that beam and splits it. And it doesn't actually physically split, but we virtually split it through superposition. So the atom is both in the lower branch and the upper branch simultaneously. Similarly, we can actually redirect those beams with another laser light pulse, which will then redirect the beams and effectively recombine them at the end to interfere. And so you can see this sort of diamond-shaped region has an atom virtually traveling through two separate paths. So if you take this diagram and rotate it in the screen, if you're rotating this, you're actually going to be changing the phase of the upper branch versus the lower branch. So if this atomic interferometer were to rotate, then the phase of the upper path and the phase of the lower path will shift and produce an interferometric pattern. And because of the wavelength and because of the nature of the cold atom, you have a much more sensitive means for measuring rotation and similarly acceleration as well. So this fundamental technique, this fundamental aspect of the atom being able to be in a superposition allows you to generate a device that can measure rotation and acceleration with a great deal more sensitivity than anything that's, you know, even photonic based, which is itself a fantastic device, but you can go even further by factors of 100 to 1,000 better. And as I mentioned before, this is an atomic-based reference. This provides capability down the road of being able to navigate for months without GPS, and you can stay tracking within, you know, tens of meters or meters depending on the application. So related to this, the other element that we talked about that's part of the inertial navigation system is time. We need to measure time accurately in order to be able to provide guidance. We need to measure time accurately in general. And in fact, time is a key element of many types of systems being able to track time. So we'll talk about this a little bit again in the context of markets and products, and then talk about what can be done with cold atom systems and where can we address this. So again, pulling that tile from the previous presentation, We're just going to talk a little bit about this. This represents just almost a $500 million market for these types of products. And this just gives some examples. This is what's called a rubidium cell clock. And what's inside here is a sample. It's actually rubidium, which is one of our favorite atoms because it's an alkali and it has a very simple atomic structure. So these are used to measure time. These can be ruggedized for rough applications. Another alkali is used called cesium, and this is put into a beam. And this kind of clock is a very standard reference that if you are in the circles of talking about frequency references, you'll hear that come up quite often. And it's notable, and I think this was brought up in some previous talks, the second is actually defined around the energy levels of a cesium atom. A cesium atom, the lower and upper states are connected by a 9.2 gigahertz microwave signal. And if you look up, well, what is a second? It'll tell you it's a cesium atom, and it's 9.2 billionth of a cycle. Another type of system uses hydrogen, and it's called a maser. And again, we won't go into detail on this. It's a very large system, but it's an even better and improved type of clock in terms of its performance and ability to keep time. And some of these can actually be put in space. So masers are actually put in space, and we'll talk more about those in our next slide. And then finally, a relatively new entrant is taking some of these devices that use rubidium atoms and makes them very small, and they make them very low power. Again, we'll talk about that in the next slide. So the area, these high performance clocks, cesium beams, masers, spaceborne clocks, these are places where cold atom based frequency references can really, these are the places where people need much higher performance clocks, and this is kind of the target area. We'll make more sense of that in the next slide, which is less market and more technical. So let me explain this plot. This is a kind of an interesting plot. This shows on the bottom axis something that you'll hear in a lot of circles, SWAP. It's the size, weight, and power. Size being the volume in cubic centimeters, the weight, its mass in kilograms, and its power. How much power does the device consume to perform its function? And those are all multiplied together to get this weird unit, cubic centimeters times kilograms times watts. On the vertical axis, TDEV has a very specific technical meaning, but there's a simple meaning. And in this particular plot, it's listed as 1 hour. So 10 to the minus 9 is a nanosecond. And so what that shows is if you follow that 10 to the minus 9 horizontal line, that means that in 1 hour, you have lost or gained a nanosecond. And if you go down, say down to the minus 10 to the 12 line, which you can see nothing on here can do quite today, you would gain or lose a picosecond for every hour that passes. So what's interesting is if you take this is a listing of a variety of different devices that measure time or frequency references of all different types of technologies. And it's quite interesting that these fall on a line. This is not there's probably physics behind it, but it is sort of, there's not a fundamental physics behind why all of these fall onto this funny line. But it just happens to be the way things fall. So here I just want to sort of call out, these end up falling into a natural grouping. So this is a very small, what's called a chip scale atomic clock. And these are used in applications such as this gentleman throwing a hand-launched UAV, personnel, human-born time tracking. And again, these aren't the greatest clocks. You can see they are the worst. Worse is up on this axis, but they are small and they don't consume a lot of power. So they kind of fill a niche for that application. These rubidium cell clocks kind of cover a range of capabilities and sizes, and these are used in a wide range of applications, including something the size of a Humvee that I show here. A cesium beam clock, we showed that before. These are a little bigger, but they're slightly better in performance. And they're used in things like submarines and other large mobile platforms. They also happen to be the timekeeper for the internet and cellular networks. So in fact, this discussion we're having right now, the packets that I'm streaming to you over my headset here happen to be controlled ultimately by a cesium beam clock. Up in space, we actually put clocks in space. The satellites, the GNSS and GPS satellites all contain spaceborne clocks, and that references time. However, on the ground, we have these larger clocks called masers, and there's some cold atom microwave clocks examples in here as well. Those GPS satellites actually have to check in with ground every few orbits. So those GPS satellites themselves actually lose time as they orbit. And so they got to check in with the ground and make sure and have a clock adjustment every few orbits or every orbit. And they do so with a ground-based clock. And it's worth mentioning that some of those ground-based clocks that everybody references to are actually based on cold atom, what are called fountain clocks. So sort of the master clocks that these masers are referenced against are also based on cold atoms. So where is the future headed? We think with what are called optical clocks rather than microwave clocks, which connect these states with laser light as opposed to microwave frequencies, can get to even better performance, maybe even off this chart, and can do so in a pretty compact package. So we'll shift gears onto our next application and talk a little bit about gate model quantum computing. And we're just going to give a little overview of this. Again, same style, talk about markets, why, and kind of put things into context. So what is quantum computing and why should I care? So a classical digital computer it has just a zero or a one. So each bit, and we call them classical bits, but the computer guys just call them bits because there weren't anything else for a long time. Can just store a piece of information. You can either say you're a zero or a one. There's not much more to it. Whereas in a quantum computing system, a quantum state can actually represent a superposition between a 0 and a 1. So it can actually store any number of values between a 0 and a 1, almost any number. And in fact, it's a complex number, but I won't get into that here. So that's just part of the power of quantum computing, is each of the qubits can represent a whole multitude of states, and those qubits can actually interact with one another. So what makes these systems so powerful? Well, because you have you have qubits and you have interference between these qubits forming gates, this allows you to solve problems that are intractable to current classical hardware. So, we can kind of make a Venn diagram here, which shows hard problems for classical computers. And this is the space of problems that classical computers can solve. And then within that, you have sort of easy problems, right? So those are maybe not so interesting, but they are the ones that they're a subset of what a classical computer can do. And then if you superimpose what a quantum computer can do, it's going to intersect both the problems that are hard for classical computers. It can do some easy problems, but then there's an area outside this circle of things that it can do that are not previously available to a classical silicon-based computer. So give some examples here, something like factorization. Now, I want to say this is something that is sometime off for quantum computers. This is not going to be the next thing, but ultimately, the belief is that we can use a quantum computer to perform factorization. This is a problem that a classical computer can actually solve, but a quantum computer can actually ultimately someday do faster than a classical computer. And then there's this interesting on the edge of what is on the edge of being possible for classical computers. And there's a whole range of applications: chemistry, material science, optimization problems, figuring out where things should be in a factory, machine learning. So again, at one level, some of these things can be done on a classical computer, but not, maybe it's, you are limited on the size of problem or the complexity of the problem that you can do, how big the molecule that you can model. And then finally, give an example, an aspect of what is possible. Things like quantum mechanics simulations require tremendously demanding amounts of memory and resources on a classical computer. So a simulation is something that is only available to the capability of a quantum computer. So what does this say in terms of context of markets? So the high-performance computing market is projected to break $40 billion. This is these huge computers that sit in, in some cases, very large rooms, 50,000, 100,000 feet, and do some of the hardest problems that you can. Some of the things we listed, very complex simulations, chemistry, and in fact, these are what's used to simulate quantum systems, but we're limited on what we can do simulating a quantum system on a cluster. And what we're observing is, performance accelerators are becoming a growing segment of that ecosystem. We have things like general purpose graphics graphics processing units. These are really great at doing vector type processing and have been a really large growth area. FPGAs have started to penetrate here too. They do special problems, they solve special problems, and even what are called large-scale ASICs have started to enter the market to solve specific machine learning problems. Ultimately, quantum computing will become a part of that extended HPC ecosystem, both in the cloud and hardware arenas. And then I show a very conservative market projection. You see from some reputable sources, and they foresee just in a few years we should be breaking $1 billion in terms of the availability of markets accessible. And this is counting applications as well as hardware and other aspects. And it breaks it down into things like materials, fintech, fluid dynamics, and pharmacy, and growing quite large by double-digit billions in just less than 10 years. So now what I want to do is sort of put that into perspective of ways that we can achieve this, right? So we talked about what is it, we talked about what are the market opportunities, and then here's just a quick overview of ways that we think about going about this. So quantum computers require high fidelity qubits. So at the outset of our talk, we talked about quantum systems and being able to have the quantum system, what we're going to now call qubits, need to be very quiet. They need to be isolated from the environment. You cannot have them interacting with the outside environment. They're exceedingly delicate. You don't even look at them the wrong way, and they end up misbehaving themselves. You need to be able to control them. You need to be able to put them into an upper state or a lower state. You also need to be able to control their interactions. There's times when you would like them to sit quietly and not interact with other adjacent qubits. And then there's times when you absolutely want them to interact with one another. You want them to entangle, which is the core of how these quantum systems work. You need them to be programmable. So that means you need to be able to get them to interact in a controlled way. And there's certain rules we won't get into. They're called the Vincenzo criteria. And these are the sort of fundamental rules you need to be able to have. You need to be able to program them, feed them instructions, have them perform those instructions, and then result in an output. And finally, you need a lot of them. We really, that's the thing we're working hard on as an industry, is to have more qubits. So one of the things I want to just show here is just to give a very, very brief overview of some of the leading hardware platforms. So you can kind of class them very broadly into qubits that are atomic, and these are identical qubits. They, as I mentioned at the outset of the talk, these are qubits that are they're created by nature. They really are absolutely identical. The only way that they are not identical isn't the way that you handle them or the way that they interfere with the environment. Whereas engineered qubits, they rely on manufacturing processes to make them what they are. You rely on lithography, and so the limits of your processing are what limits the identicality, if you will, of those qubits. Another aspect is being able to run at room temperature. Neutral atoms can actually be, we use lasers, as we said at the outset, to make them exceedingly cold. Since we're using lasers to control them and to make them cold, the overall system and apparatus can remain at room temperature. So we don't need cryogenic cooling tools. And we said before, we use lasers to control them. And so we're, some people like to say we're kind of building the fab on the fly, because we do have to, by having to put the atoms into making them perform and behave. They weren't there before, but once the lasers are turned on, they're there and they're behaving themselves. So it's sort of building that on the fly. And then optically interfacing. We do need to use lasers, and that allows us to precisely control each of the atoms in the system. And microwaves are used primarily in engineered qubits. And then finally, reconfigurability. You can actually move atoms around and change the way that you are going to use them. Whereas in an engineered qubit, you typically have a hardwired topology that's defined by the lithography of your system. Okay, so that, just to wrap up, we kind of covered 3 different areas of neutral atoms and the background. So, quantum funding is accelerating both our R&D and commercial efforts. These markets are growing. Investments coming from both government as well as private areas. The systems that are based on cold atoms have some very specific and significant advantages over other approaches that are available to create quantum systems. And then finally, these may first impact inertial sensors, clocks, and quantum computing. And I actually have one more summary slide, but there's a last slide. Give us a holler. Let us know what you guys are working on. We'd love to talk with you about your applications and requirements. We have new products right around the pipeline. Seth talked about this one at the last talk, so we really want to hear from you. What do you need? What can we do for you? And of course, there's a lot going on at the company, so stay tuned. This is really only a slice of the activity going on at Cold Quanta. So that being said, I think this is the time I hand this over. Again, I want to thank everyone for your attention and time. I really appreciate the opportunity to share a little bit about the quantum world with you. And I think it's the time to hand it to Diane.
Thanks, Rob. That was great. We do have a few questions to ask, and if anyone else has anything they're interested in asking, we do have some time on the clock, so go ahead and submit those in the Q&A box. So our first question is, why are optical clocks so much better than microwave clocks?
I'll give a simple, rough answer, and I think this might get addressed in great detail in a future talk, but the difference has to do with what's called Q, or quality. A clock is really about making a great resonator, and the quality of that resonator has to do with the fundamental frequency that connects these energy levels. So one of the fundamentals is that these microwave clocks are typically running the frequency that connects the levels is, call it 6 or 9 gigahertz. Whereas if you have an optical clock, now you're actually in the, I'm going to get my numbers wrong here, but I think it's in the hundreds of terahertz or more. So your factors of many factors of 10 larger, which is what makes an optical clock fundamentally better. And I think that's all I can do for this one. I want to point to a talk that will be given shortly that will give it in much more detail with a little more technical depth.
Okay, and the second question is, if you have to manipulate atoms with lasers, it sounds like this would be a really delicate instrument. Can you actually make these things rugged enough to put into an airplane or space?
Good question. Yeah, so the lasers themselves, they're it sounds delicate, but the reality is, as mentioned at the outset, we're actually, the atoms are being pounded by the lasers at the tune of 1,000 G. So the kinds of forces that are actually holding the atoms in place are quite high. So the aspects of making things portable and rugged have a lot to do with the instruments and the way that you build the entire system. And something we didn't go into detail here is one of the things we've spent a lot of energy as a company on for quite some time is making the systems very small and making them compact. And by making them small and compact, the lever arms, which make things bend, can be made much smaller. So that is in fact one of our focuses, is trying to make things smaller so that they are more rugged and more capable of being deployed.
Okay, and what are some of the practical or commercial applications of higher precision clocks?
That's a good question. I don't want to steal the thunder of future colleagues. There's applications where maybe I'll verbalize this one, wherein you want to be able to measure time in a moving system, and by having a very accurate clock, more precise than what we can do today, you can actually figure out your location more precisely than you can with the clocks that we have available today. So it allows very precise location on the Earth. And one of these applications is something called phased array radar. And you need to know your location to very tiny distances. This is micron, a millionth of a meter type of distances. And when you get to those kinds of applications, you start to move into a place where traditional clocks are not going to be sufficient to give you that kind of resolution.
Okay. What are the effects of subatomic particles and what they play on cold atom technology?
I'm not sure to answer that question. I guess I can just state, subatomic particles, if the question is about sort of the quarks and other leptons that make up the atoms, those are within the atoms and within the protons and neutrons. I'm not actually sure how to answer that question. I'm sorry.
Okay. So panel, are there any other questions that we have for Rob? Okay, here's one. Can you please elaborate on the realistic timeline of developing a working quantum inertial sensor? I.e., can you give a lab sample? And how would you mass produce such a device?
So these are devices that are being, these are the laboratory devices do exist today, and I think we're in a developmental phase with these devices in terms of being able to demonstrate. And there have been demonstrations that actually use some of our hardware integrated into systems that show doing measurements of the full measurements of, for example, a gyroscope and measuring rotation rates and the various parameters that characterize them. So we're still, I think it's still, we're still in development today as an industry, and a lot of more, a lot of development. There's still development needed to move things forward.
Okay, is cold quanta active in the field of quantum communication, QKD, or do you see that as uncorrelated to cold atoms?
Good question. We actually have some programs ongoing today that are related to quantum communications. I don't have slides to speak to that today, but we do have a couple of development programs involved in that specifically, but I'm not at liberty to give all the details of those programs. They're still internal R&D programs.
Okay. Can you point to which one of these markets makes sense for a startup to enter, something that would be low-hanging fruit?
I've kind of painted a picture of the overall markets. So I think we might be getting a little bit into our own company strategy. So I think it's a great question, but I'm going to defer on that one.
Some of these are getting pretty specific. Are you targeting any ruggedization standards, a la millispecs, tetraquadral, NEBs, etc.?
I know what some of the mill standards are. There are some, I guess something that we did not mention in this presentation, but has been mentioned in the past. Some of the subsystems that we build are actually orbiting on the space station. So we actually have gone through, qualification and ruggedization of, in fact, the graphic you're staring at right now is indeed one of those systems. So yes, we have qualified to certain specific customer requirements. For very specific systems. On the second part of that question, I'm not sure I don't know what that term means.
Okay, this will be our last question. What components and enabling technologies does cold quantum manufacture that are used in a cold atom gyro or accelerometer?
Good question. Well, today we span a variety of pieces. We have built quite a number of cold atom, systems in the sense that they involve vacuum systems, the optics, integration of the delivery of the lasers into the system, and in fact, all the way up to full turnkey systems. And so maybe referring back to the space station program, that actually, that program is, in fact, the one that was most recently launched is actually the elements of a atomic interferometer and therefore an inertial measurement system, and that has some of our components, and then working with JPL and NASA has all of the pieces. So that you can consider that to be an early stage deployed system.
I lied. There's one more question. They actually keep popping up. So, with the potential of the rise of 5G, what role or impact will quantum computing have in that market?
That's a good question. I think maybe speaking very broadly here, I mean, 5G is primarily to make high-speed communications ubiquitous, right, and make things accessible to folks. So I think one of the impacts of 5G, as it might relate to quantum computing, would simply be that access to quantum computing resources as quantum computers become to be available and start to become useful down the road, 5G will be a piece that will make that resource available to you, anywhere you go.
Okay, so I think that was truly our last questions. Please continue to send any questions you have, as we will email responses. So thank you once again for joining us, and thank you, Rob, for an excellent presentation. I really, really enjoyed it. And as we said, we will email the link probably early next week to everyone who registered, and it will also be available on Cold Quanta under the Events tab. So everyone have a great rest of the week, and we'll see you in our next webinar. Thank you.
Thank you.